Good morning. Let's begin today's module with a practical example of the use of continuous random variables. In particular, we will look at cumulative density function and its uses. The example here talks about the length of time to failure for a certain transistor, which is defined as a random variable with this cumulative distribution function, which is given by this uppercase f of y, which is 0 if y is less than 0 and 1 minus e raised to negative y squared if y is greater than 0, which means this density function is really defined only on the positive side of the real line, and anything below 0 it is going to take a value of 0. And the question here is they are asking us to show that f of y has the properties of the distribution function. And if you recall, we talked about three specific properties of a distribution function, and we need to prove for this problem each of these three properties. And the first property is listed here, which is limit f of y, where y tends to negative infinity, is equal to 0. And the second one is limit y tends to positive infinity, f of y, we need to prove that is equal to 1. And when we choose two constants where b is greater than a, we need to compute f of b and show that it is greater than or equal to the value at f of a. So these are the three properties of a cumulative density function. Proving point 1 is pretty straightforward, because if it is 0 for any value less than 0, then obviously at negative infinity it is going to be 0. So proving that is pretty straightforward, and that is what is shown here. The function becomes 0 immediately after 0, therefore the limit of that function at negative infinity will obviously be 0. Let's prove number 2, which is limit y tending to positive infinity, f of y, which is limit y tends to positive infinity 1 minus e raised to negative y squared. So I can bring the 1 outside, minus, you take the limit within, limit y tends to positive infinity e raised to negative y squared, or 1 minus e raised to negative infinity, because you substitute the value for y as infinity, and that becomes negative infinity. And e raised to negative infinity, we know that that value is 0, so 1 minus 0 takes a value of 1, and that's exactly what we have here. For proving part 3, or the property 3, we need to pick a b which is greater than a. So I picked a b which is 3 and a equals 2. You can pick any other values, and then we are essentially trying to find f of 3 and f of 2. So all we need to do is really substitute that value in e raised to negative y squared, and that happens in this case to be when you have 1 minus e raised to negative y squared. If I substitute in place of y either the value of b or the value of a, I will be able to compute f of 3 and f of 2, and this calculation can be done using your calculator or Excel or MATLAB. And 1 minus e raised to negative 9 is 0.9998, and 1 minus e raised to negative 4 is 0.9816, which clearly proves that f of 3 is greater than f of 2. The next part of the problem is asking you to find the probability that the transistor operates for at least 200 hours. This is really a scale value, so let's just talk about 2 hours and not 200. So at least 2 hours means that you have to find the probability that this transistor is operating for greater than or equal to 2 hours, right? Or you can find 1 minus probability that y is less than or equal to 2. So you can find this value. So what you can do is, there are two ways to do this. One way is using the probability density function, where you can find the original function, not the cumulative distribution function but the density function, which you can obtain by differentiating the cumulative density function and then integrating that function between 2 to infinity, and you will have to end up using integration by parts because we have two y terms in this integration equation. Or the easier way, especially for this problem, is to directly use the cumulative density function, where it really turns out to be 1 minus f of 2, because this probability of y being less than or equal to 2 is nothing but f of 2, because you're trying to find the probability up until that point 2, and 1 minus f of 2 is nothing but 1 minus e raised to negative 4, and that's exactly what we have here, and that happens to be e raised to negative 4, which is 0.0183. That's how you compute or answer questions using the distribution function of a continuous random variable. Here are a couple of other examples that talk about some practical applications of using continuous random variables. So I have divided this page into two halves. In the first, on the left hand side, you have a density function of a random variable. X is f of x, such that when x is greater than 10, it takes a value of 10 divided by x square, and anything less than 10, it is 0, which means this function really does not exist. To the left of 10, this function does not exist. It only takes values beyond values of 10. So the first question is to find the probability that x is greater than 20. So you essentially take this density function and integrate between the limits 20 and infinity and find the value. The reason I'm not going over this in detail is I want you to take a look at this example. This notes is available on D2L, and you can go over this example and email me if you have any questions. On the right hand side, we see another example of another random variable, the density function of another random variable x, which is defined as c times e raised to negative 2x, and this is a positive function. Once again, it is defined between 0 and infinity, and below 0 this function takes the value of 0, which means it does not exist on the negative space. And the first part is to find c. If you remember, if you recall from one of the previous modules, we covered how to find a constant. We found the value of k, if you recall, and all we need to do is really take this density function and equate it to 1 and find the missing value c. And if you have to find the probability that x is greater than 2, all you need to do is, once you have the value of c, you need to integrate that function between 2 to infinity, and if I pull the c outside, you have a e negative 2x dx, and that should give you the answer for that. And once again, I want you to try that as a quick assignment. Why don't you take a pause now and actually go ahead and try those two problems, and then you can always refer to D2L for the correct answer. And if you have any questions, once again, please feel free to email me. So the next topic that I want to talk about is mean and variance of random variables. The reason that I'm covering all of this material very quickly is that I just, this kind of a refresher. I don't want to spend too much time talking about probability and random variables, but if I teach statistics, a class in statistics, without talking about random variables and probability distributions, then that would not be a good thing. And I feel that there's a much better way to teach you guys the basics first, and then we'll build on the basics as we go forward. You'll look at several topics, like I said in the first lecture, or the introductory module, where we know we're going to talk about regression. We'll talk about some design of experiments, some quality control. So all of these topics really need probability and random variables as the basics, because we have to go from probability to random variables and then to statistics. So let's talk about expectation of a random variable. The expectation simply means the average or the mean. Just like how a set of data can have an average or the mean, a random variable has what is called an expectation or the expected value, okay, which is always represented by this uppercase E, and within square parentheses the random variable that you're trying to find the expected value for. It is defined as summation x such that f of x is greater than 0 x f of x. The expectation is really kind of the weighted average of these random variables. Let's start with there's a definition for, bear in mind, there's a definition for a discrete random variable. Okay, so that is very critical to understand, and that's the reason we have this summation and not an integration sign, which we'll look at for continuous random variables. For example, let's define x as the roll of a die. Once again, if you recall what the space is, we have 1 2 3 4 5 and 6, which is the space for that random variable, or the sample space for that experiment. And if you want to find the mean or the expected value of that random variable, all we need to do is apply this formula. In this case, when we talk about summation x f of x, we are really talking about x means the value that this random variable could take, which means in our case this random variable could take a value of 1, it could take a value of 2, it could take a value of 3, it could take a value of 4, it could take a value of 5, all the way until 6, and each of those x's is multiplied by f of x, or the probability that this x actually takes that value, which means the probability of getting a 1 is 1 over 6, probability of getting a 2 when you roll a die is 1 over 6, the same probability for 3, same probability for 4, 5 and 6 and so on. So when you actually compute this, you will end up with a value of 7 over 2. But bear in mind, expected value is simply the mean. It doesn't mean that you really do not get a 7 over 2 when you roll a die, but that is what we call the expected value of this discrete random variable. We can use the same idea for the expectation of a continuous random variable, which is e of x is nothing but the integration between negative infinity to positive infinity x f of x. Previously, if you recall, we had summation x f of x, and the summation is now replaced with the integration. Okay, the summation is really replaced with this integration, but the idea still remains the same. Just like how we can compute the mean of a random variable, we can also compute the variance of a random variable, and it is typically represented as sigma squared, or v, and it is defined as e, the expectation of x minus mu whole squared. So if you recall from your high school statistics or your undergraduate course in statistics, sigma square is usually defined as summation x minus mu whole squared divided by the number of values, right? And the summation of these x's divided by n is nothing but the expectation, and the expectation of x minus mu whole squared, if I expand the x minus mu whole squared, you get x squared plus mu squared minus 2 times x times mu, and the expectation can be taken inside, plus mu squared, expectation of mu squared is mu squared because expectation of a constant is a constant, minus 2 times mu times e of x, which is expectation of x, and once again we simply get e of x squared plus mu squared minus 2 mu times expectation of x is once again a mu, so that becomes 2 minus mu squared, and the final formula is really expectation of the variable x squared minus mu squared. Or in other words, this can also be written as expectation of x squared minus expectation of x the whole squared, and this is nothing but the mu value that we just talked about. Okay, so the variance value can be easily determined using e of x squared minus e of x the whole square. And remember, e of x squared, if you have to compute e of x squared, it is nothing but, for a discrete random variable, it is simply summation x squared f of x. If you had to find, for example, expectation of e of x cubed, that was simply summation x cubed f of x. So the idea is same. E of x squared is called the second moment. Okay, these are called moments. Here you have a solved example for calculating the variance of the roll of a die. Once again, sigma squared is nothing but expectation of the variable x squared minus mu squared, and I computed these individually. Once again, I want you to give this a shot by yourself without looking at the solutions. While this is posted on D2L, I want you to first solve this yourself and then take a look at this. It is pretty straightforward. The calculations are very straightforward, just based on the formulas we talked about. So once you solve this, you will be familiar with how to compute the variances and expectations of discrete random variables. And what we will do is we will begin our discussion now in the next module with probability distributions and the most commonly used probability distributions.